Welcome. The title of today's notes worksheet is Circular Motion Day 2, and the objective of today's lesson is really just to review some of the formulas and strategies that we looked at yesterday dealing with a point moving in circular motion. So we'll do exactly that piece, as you can see on the paper there. Just have a little review to get some of the ideas going, and then we'll just do some examples to solidify some of the concepts from yesterday. So let's start it out right away here. There's a review at the top, and it says for letter A, what is the formula relating the arc length of a circle and its central angle? And so in this particular case, if you remember correctly, this was the S over R is equal to theta, or S equals R theta. So that's the connection between the arc length, the radius, and theta. Please just remember one thing with this one. As great of a formula as it is, theta must be in radians for you to work with it. So theta in radians for that one. Okay, then letter B. What is the formula relating the linear speed of an object in circular motion and the angular speed? And if you remember correctly, the linear speed we denoted with V. And let's catch it here. Angular speed, if you remember, we denoted it with that lowercase omega. We really just called it W, as it looks like a fancy W. So the formula relating those two, again, fairly simplistic to work with, and it's V equals RW. And if you remember yesterday, we basically used this formula here and a couple definitions about linear speed and angular speed to come up with the relationship between the two. So this produced this right here. Okay, so that's how we'll go from linear to angular, or angular to linear. And remember that idea, as an object moves around a circle, really there is that central angle tracking it. And that central angle has a speed just as the point has a speed. Okay, let's do letter C. How do you convert from revolutions per time period to radians per time period? And so in this particular case, think about it this way. I have revolutions over time. And again, you don't have to necessarily write this down. But what is it that I'm going to do in order to change revolutions to radians? And again, you can wait just a second here. Let me develop a couple things, and then we'll write down exactly what we need. But basically, if I want to change revolutions, to radians, I'm going to talk about revolutions on the bottom and radians on the top. These would then cancel, and so forth. So what is the dimensional analysis that allows this to occur? Well, very simply, remember 2 pi radians is the same as 1 revolution. So to go from revolutions per time period to radians per time period, which of course we do know to be W, we're going to multiply by, and this is definitely what you'll put on your paper, multiply by 2 pi radians over 1 revolution. So it's just dimensional analysis, changing the units without changing the value. Great. And in letter D, it looks like we'll want to reverse, of course. How do you convert from radians per time period to revolutions per time period? And again, just hold off a sec if you want to just kind of peek at what I'm doing up here. I have radians per time period, and I want to go revolutions per time period. Well, again, there's dimensional analysis that allows this to occur. If I have radians up here, I'm going to need to cancel that out down below. And so you can kind of see the dimensional analysis in place. We have the fraction that we're going to want to multiply by, because 1 revolution is the same as 2 pi radians. So I guess this is what we'll write. We're going to multiply by 1 revolution over 2 pi radians. Now here's the one where you have to be just slightly careful. So please, on your paper, make sure you emphasize that piece. You do need parentheses around that 2 pi radians in order for the calculator to give you the proper answer. So 1 revolution over the whole 2 pi radians there. And that's pretty much it. Those are the 4 things that you will be developing for every single problem you do in circular motion. So let's give it a try. Let's do, I think, it's either 3 or 4 examples here. And let's see what we have. So example 1, everyone. It says, how far north of the equator is New York City if it is 40.714 degrees north latitude, and use 3,961.3 miles as the radius of the Earth. So although the Earth is not perfectly spherical, it's close enough where we can use an agreed upon radius. And I looked online. This is the most recent and the most accurate that I found. So we'll go with this one, 3961.3 miles is the radius of the Earth. So let's sketch it out here, just get a sense of what we're looking for, and then maybe something will pop up. So as best as I can, I'm going to draw the Earth right up here, something like that. And I'm going to draw the equator right smack in the middle there, something like this would do. And basically we'll just throw New York City right up here, give or take. And so if you're unsure how latitude works, it's all based actually on the central angle with the initial side. And actually let's get that initial side. So the initial side going to the equator and the terminal side going to the point on the surface of the Earth that we're looking for, in this case New York City. And so latitude is just based on this central angle right in here. And so the way I see it, everybody, is when it says 40.714 degrees north latitude, you can see obviously north of the equator, the central angle created right in here is going to be 40.714 degrees. Something like that would do. So that, everybody, is going to be our central angle. I'm given the radius of the Earth, as a matter of fact, and you can put it in one of two spots here, but this is the 3961.3 miles. And what I'm looking for, if you read the question, it says how far north of the equator is New York City. So you can kind of see this situation right here. We are looking on the surface of the Earth as it being an arc length. So how far north are we? What is the distance directly from the equator to New York City? On the surface of the Earth, that would represent the arc length that you see in this diagram. So you can see the situation at hand here. I have a theta, I have an r, and I do need s. Now, so you know right away that is going to be our formula. And as I said, for all of these, you're either going to use s equals r theta or v equals rw. As you can see, it's this one. And we just have to be careful about one thing. I certainly have the radius, which is absolutely great. The only problem, of course, is this angle right in here, which was expressed in degrees. So I cannot use that in this particular formula. So everybody, please, let's think about it off to the side for just a second. I want to change 40.714 degrees, and I want to change that into radians. So here, again, just good review, always rehashing old things. There's a lot of spiraling in this curriculum, as you'll see. But basically what I would argue is, well, I would ask you, do we want to go pi over 180 or 180 over pi? And if you remember correctly, to change degrees to radians, we want to multiply by pi radians. And again, you can put the RAD or not, your call, over the 180 degrees. And so everyone, if you would, let's cancel these out and grab your calculator for me and just take a moment and do that precise calculation. So let's see what I have it to on my paper here. I have it to about 4 decimal places. And if you get an opportunity, can you take 40.714 times pi divided by 180? And if you do that, you should get about this, give or take. So that's how many radians it would be. And again, you can put the RAD on the back or not. It is a unitless value. So just as a real number, that is the angle measurement in radians. Perfect. Now, guys, let's go ahead and put it in. I think we're ready to roll. So S equals 3961.3 miles times the 0.7106. And remember, I do units with everything here. In this case, I have miles just times the real number, so I'm actually not changing my units. The radius units will be, of course, the same as the arc length units, and we kind of looked at that piece before. And so, again, I would ask you to just grab your calculator there and do 3961.3 times 0.7106. And I get something along these lines right here. I get about 2814.87 miles. Excellent. So, again, a great formula. Really nice and straightforward to work with. You do have to make sure that you put it in radians, of course, before applying it. Otherwise, you get something that really doesn't make a whole lot of sense. And remember, of course, you should be getting better and better and starting to see degrees and radians together. 1 radian was about 57.3 degrees. So, 40 degrees is certainly less than 1 radian, as you can see right there. Okay, good. Let's go on to example 2. So example 2, let's see here. A merry-go-round spins at 10 revolutions per minute. And here's an interesting, just conceptual question. Which travels faster, a seat 5 feet from the center or a seat 15 feet from the center? Or do they travel the same speed? So I guess let's kind of sketch it out, think about it for a moment here. If you have an answer already, that's great. But basically, I would argue you've got sort of the 5-foot seat kind of making this circular path as it goes around the merry-go-round there, something like this. And then you have, ran out of room there, but something like this would do. And then you have the 15-foot seat. So out here, same idea. That's going around in a circular path. And I don't know, I'm going to just kind of do this. I don't know if that'll be helpful visually or not for you. But basically, each one of those is able to make 10 revolutions in a single minute. So again, 1 revolution, 2 revolutions, etc., etc., 10 in a minute. This one up here, everybody, 10 revolutions in a single minute. And so the question is, in terms of the speed, how fast it's moving around that circular path, is there one that is faster than the other? And if so, which one is it? Well, I guess here's how I would describe it, and certainly if you want to write it down differently or think about it from a slightly different perspective, of course that's fine. But I would argue that it has to be the 15-foot seat. That is moving faster than the 5-foot seat. And here, I guess, is the argument behind that. Each of those points, this one right here, so think about the seat right there and think about the seat right there. Each of those seats is making 10 revolutions in a single minute. But if you look at it, this one has to cover quite a bit more distance in a single revolution. So in other words, if it's traveling a greater distance in the same time, it has to go faster in order to do that. Whereas this one right here, this one has to travel a smaller distance in the same amount of time. And so if it's traveling a smaller distance in the same time, it can do that in a lower speed. Okay, so I think the farther it is out, the faster that it's moving in circular motion. So I guess what we'll do here is just find the linear speed of each seat, and we can sort of prove this and show this mathematically, and then we'll go from there. Okay, so I guess the first order of business is this. Each seat, so I guess we can start it out the same way. The information that I know is 10 revolutions in a minute, and this is that continuum we talked about on the previous notes worksheet. If I have the number of revolutions, the next quantity that I'm going to be looking at is the angular speed. I'm going to go get W. And how do we go from revolutions to radians, everybody? Well, again, we did this on the review. 2 pi radians is 1 revolution. And so revolutions are going to cancel here. Again, units with everything, quantify everything. I get 20 pi when all is said and done. Radians per minute. Again, that unitless value there. And I'm going to go ahead and put equals W. So for each of those, the angular speed is going to be 20 pi revolutions per minute. So you can kind of see this as best as possible. As these 2 points move around the circle, the angle that's tracking them is moving at the same speed because it's the same terminal side going through those 2 points. So as the number of revolutions is identical, the angular speed for those 2 points will be identical. But as we have talked about before, and this bears it out as well, the linear speed is not just dependent on the angular speed, but it's also dependent on the radius of the circle. The farther out, the faster it's going to go. And so I think we'll just do a V equals RW for each of these. I'll tell you what, if you don't mind, can you calculate one for me just without my assistance? How about you do the inner seat, and I'll do the outer seat, and then obviously I'll have to write the other one as well there. But I'll go through at least the motions of getting the outer seat taken care of. So remember V equals RW. And again, if you feel like you need to pause the video for a minute to do that, that would be great. So I'm going to do the outer one, and I see the radius is 15 feet. Angular speed is 20 pi. So 20 pi radians per minute. And when I do that right there, again, I end up getting feet per minute. For the outer one, if I do 15 times 20 times pi, I rounded mine. I have about 942.48 feet per minute. Okay, so that would be the outer seat, and that's how fast it's traveling. Now the inner seat, of course, is just putting 5 in here and multiplying it by the W. And I'm hoping you did that one. And you would see, of course, again, the closer it is to the center, the slower that it goes. And in this particular case, I end up getting about 314.16, give or take, feet per minute. So those are your two linear speeds right there. I'll box those up. I have a lot of stuff up here, so I'm going to box those up to just separate those a little bit up on the board. And those are your two. And notice just the relationship, of course. You can kind of see that the outer seat is 3 times greater, 3 times farther out than the inner seat. And as a result, if you kind of look at the linear speeds, that outer seat is going 3 times faster than the inner seat. And so they are what are called directly proportional. Okay, good. Let's do part C. It says convert each answer from part B to miles per hour. So I feel like that's a better unit when we talk about speed. It just has a little more meaning. So 942, I'm going to start with that one just to give you a heads up on how that works. And then obviously you guys do whatever you need to do on the other one. But I have 942.48 feet per minute, and I want to change this to miles per hour. So remember, get rid of feet, 5280 feet, and 1 mile there. That would be that case. So feet would cancel. And then I want to change minutes to hours there. So how about something like this, 60 minutes and 1 hour. If you have any issues at all with the dimensional analysis that we've been working on, and we've been doing a lot of it as a matter of fact, obviously please let me know. But it looks like if we do that, we end up getting miles in hours. So I would take my 942.48, multiply by that 60, and then divide by that 5280 there. And if you do exactly that, this is the outer one, it's going about 10.71 miles per hour. Wonderful. If you repeat the process there, same thing. I guess what I'm going to do is just put that 314.16 so we can get this moving along here. And again, kind of like a dot, dot, dot. Same idea exactly, just kind of convert that over. And we should see, really, again, all you need to do is divide this by 3 because that's the relationship. But it would be, as you can see, a factor of 3 less than the original there, the faster one. So 10.71 and 3.57. Wonderful. So again, in my opinion, just an interesting conceptual problem there, talking about the fact that the distance away from the center of the circle really does affect the speed at which it moves in circular motion. Okay, good problem. So revolutions to radians and to that linear speed. Okay, let's see. Example 3. How fast is an object at the equator traveling as the Earth revolves? And use 3961.3 miles for the radius of the Earth. Okay, great. So by the way, we're going to see a variety of these types of problems in the future. In fact, example 1 is kind of a prelude to that. But let's kind of see what's going on. The only way we can start this at this point is really to talk about a point on the equator and traveling in circular motion as the Earth rotates. So something basically like this, for lack of a better description. Here's a point on the equator, and if you can envision this, of course, as the Earth rotates around, that point is moving in circular motion. And again, if it's covering a distance over a certain amount of time, it's traveling at a certain speed. And that's what we're looking for here, of course, the linear speed. And so as you can see in the problem, what's kind of interesting about this is we don't really have a whole lot of information. It's not much to work with here. I have the radius, which is great. That's kind of the default part, but I don't have much else. So if you think about the quantities for a second, what do we know, even though I didn't write it here for example 3? Well, I guess here's what I would say. By definition, as a point moves in full circular motion, it is able to achieve 1 revolution in a full day. Or, and just to kind of get this going in the right direction for us, really 1 revolution in our 24-hour increments of that day. So even though it's not written, that seems to be the case. 1 revolution is 1 day. And so 1 revolution in 24 hours, And now all of a sudden it comes out. I'm able to go from revolutions to W and then to V. And so that's exactly what we'll do just one more time here. So let's play it out, of course. And so I would say 2 pi radians, 1 revolution. Revolutions are going to cancel everybody. And you end up getting 2 pi over 24 radians per hour. If everyone's okay with this, I'm going to go ahead and just reduce the 2 pi over 24 as to pi over 12. And again, anything I do has units attached to it. That way I know everything is consistent. So pi over 12 radians per hour, and that is our W. And again, if you really think about it, no matter where you are on the surface of the Earth, and by the way, here would be kind of the terminal side tracking the point as it moved around, no matter where you are on the surface of the Earth, this quantity is the same, 1 revolution in 24 hours. And as a result, everybody's angular speed is pi over 12 radians per hour as that terminal side of the circular motion moves around, as that changes. And it changes at a speed of pi over 12 radians per hour. Okay, but of course, the linear speed is not just dependent on W, it's also dependent on the radius. And so let's talk about this particular case here. Let's get V going. Once we know W, we've got the relationship to pull this off. And so everyone, 3961.3 miles. And then times pi over 12 radians per hour. And again, radians being unitless, that's just kind of sitting there. It looks like we're going to get miles per hour, which is perfect, exactly what I wanted, which is kind of why I changed that when I said 1 revolution in a day. I knew we were probably going to go hours with this, so that's why I went 1 revolution in 24 hours. Everyone, if you can just grab the calculator there, and let's see 3961.3 times pi and divide by 12. And let's see what we end up getting there. I did it on my calculator, and I got something like this, about 1,037.07 miles per hour. Again, make sure you're able to kind of see that piece. And so again, as a point on the equator is moving in circular motion, it's traveling at 1,037.07 miles per hour. Pretty cool. Now, example 4, we're not going to do any math with at all, but we are going to at least set the precedent here because we are going to see this problem in the future when we have a little more of a background with it. So let's read it and start to wrap this up. Will an object in Boulder be traveling faster or slower than an object at the equator as the Earth revolves? So again, I'm a very visual person, so I'm at least going to get some type of setup here. If you can just peek up here or draw it, it's totally your call. So that's what we just did. There's a point moving in circular motion at the equator, looking great, and we found out its linear speed. Here, everybody, here would be the point up in Boulder, right here, again, working in circular motion. Has the same angular speed because, again, it's 1 revolution in 24 hours. But what about the linear speed? Do you think us in Boulder, do you think we're traveling faster or slower than somebody down here at the equator? And if you think about one of the problems we just did about 5 or 10 minutes ago, well, basically I think we can come up with the fact that it's probably slower than an object at the equator. And why is that? Well, I guess it's the same logic there. As a point moves in circular motion in Boulder, look at the circle that it's traveling around. It's a smaller circle than the one at the equator. And so again, it's traveling a less distance. It's traveling less distance in the same amount of time. So in order to do that, it's going slower. At the equator, obviously, it's the largest circle on the surface of the Earth there. And so it's traveling, has to travel faster in the same amount of time. Perfect. So it has to be slower there. We're actually going to calculate that, as I said, in the near future, but there are a couple things we're missing. I'm just going to add a couple ideas to the diagram here just so you can see. What we are missing, by the way, is this piece right here. We're missing the radius of the circle that Boulder is traveling around in circular motion there. So we're missing that R. We were fortunate enough in this one that this radius obviously is the radius of the Earth. That's the 3961.3. But what we don't have is this R right up here. That's not 3961.3. So I'm just going to add a couple things to this diagram here and show you what we're going to do eventually. But if I sort of sketch a couple ideas in, here, remember this piece from the center of the Earth to Boulder right up there, that would kind of help us with the latitude and all that stuff, which we'll use. But basically, and I'm not doing this justice up here, when we do it in the future, I'll draw a much better diagram. But basically, we need a little right triangle trigonometry to pull off that. So we're going to utilize some right triangle trig in order to get the radius of our circle as we travel around in circular motion. And once we do have our radius, oh, we're good to go. And as a matter of fact, just FYI on this, we're going to be able to calculate or actually come up with a function, a trig function, that allows us to calculate the linear speed for anywhere on the surface of the Earth very quickly. And it's all dependent actually just on the latitude. So linear speed dependent on latitude. So some good math there that we'll take a look at in the future. But for right now, I think we'll leave it at this. Okay. Well, again, just some good stuff with circular motion here. Get some practice on it. If you find some shortcuts for yourself, great. Just run them by me and make sure it just works for you. Thanks for listening, of course. I appreciate it. And let me know if you have some questions as you move forward.